or move the camera back so I can use more of it, but.
If the ceiling was just slightly high, you could have the electrical one and have several things and just put it up.
Yeah, it'd be the big lecture halls where you just pull down the next one and. Right on.
For the tension in the lab, do we use this formula, or is tension equals to the hanging mass times gravity?
It's the weight of the hanging mass, so mg.
So,
Yeah. And in a localized area, the tension's going to change slightly, but it shouldn't be a significant change in the tension.
Just want to make sure I heard that right. So the tension is equal to mg, right?
In the lab, yes.
Is that the formula that was on the sheet?
Yes, I believe so.
Okay. I can remember.
Got one right here. Oh, no, that's the 110 version. Oh, there we go. Yeah, on the sheet here, instead of doing F sub t, I did t because I hadn't switched out that notation. All right. Sort of another miscellaneous topic. Resonance. From the simple harmonic motion lab that you did 2 weeks ago, a week and a half ago, almost 2 weeks ago, you had a slate key, you pull down a certain amount, you let it oscillate back and forth. There's a natural frequency to this. Now, I'm just holding it still right here, but I can accentuate it or dampen it, depending upon how I do it. But if I just sort of shake my hand, that really doesn't do much to the overall, doesn't do much other than just make it travel strangely. But suppose I move my hand with the same frequency as the natural frequency. What's happening to the amplitude?
Doubling.
All right, or increasing. So we have a driving frequency that if it matches the natural frequency, we get this thing called resonance, and the oscillations get bigger and bigger. Now, when I was undergrad doing engineering, there was a professor talked about there was a store in downtown Durham that kept losing customers, and they were trying to figure out why. And they interviewed the customers, and the customers, there was a common theme of the customers always felt a little bit stomach sick every time they were in there. And so they brought engineers in eventually. And the engineers started doing testing, and there is a sort of a average natural frequency of the human stomach that happened to match the natural frequency of the floors in the store. And so as people walked, it wasn't enough to make people sick, but just make people feel a little bit off. Because when they walked on the floor, the vibrations would then get to the stomachs, and the stomachs would slosh around just a little bit more. And so what they did is they dampened it. They changed the natural frequency, so that was not an issue anymore. And then personal experience of, I grew up in Richmond, Virginia, and there was a bridge as we would go over to my grandparents' house. And bridges have a natural separation in there so that in the summertime when it expands or wintertime when it contracts, that it doesn't get messed up. So they have these things that drive over a bridge, you hear that as you go over them. I got a couple of nods there. All right. They were spaced so that when we got to the end of it, we were bouncing a little bit more than when we started, because we had the first one, we did the boom, and the second one was timed just right, or spaced just right, so that it sort of matched the frequency. So, as a kid, it was a lot of fun. You're bouncing a little bit more than you would normally, probably not as much as that, even though my memory wants it to be. and it wasn't enough to damage the cars.
George, in the thing you wrote in green there, yeah, in the first line, in the top, yeah, you got a secondary derivative, that divide a second derivative, then, and then you, suddenly, you got now, yeah, no, a square, now you got a square of this p, of the, yeah, an acceleration, that's an, dv dt is an acceleration.
That's an x, that's dx dt. That's dx, and that's dt, I should say.
Exactly, yeah, then, yeah, okay, dx, dt, the second derivative is your acceleration, no? But how come you got a square now there?
Alright, so this right here, this is so this fraction right here, dividing one fraction by another, this is d squared y dt squared times the reciprocal of that one, which is dx squared d squared y.
Yeah, those cancel.
Those cancel, and what I'm left with is dx squared over dt squared. But remember where this comes from. If I've got the derivative of, let's just say dx dt, let's just use different letters there. So I have p as a function of q. So I take a derivative with respect to q and get dp to q. If I take the derivative of the derivative, then it's d dp to q over dq, which we typically write as d squared p dq squared. That's the typical way of writing it. But recognize this dq squared here is dq times dq.
I thought that that was the second derivative of.
This is the second derivative of p with respect to q, but since the d squared y's cancel out, the change in y, we're left with dx squared. This is dx times dx, and this is dt times dt. In other words, that's dx over dt squared. When we put in the intermediate step, that becomes dx over dt times dx over dt.
But in green, what you have on the numerator is a second derivative, no?
Yes, it is.
And in the denominator is also a second derivative?
Yes, it is.
Then how suddenly a derivative become a square instead of second? It's still I don't know if I'm missing something, but I will have written that like the second derivative of x.
So d squared y dt squared is d dt of dy dt.
Exactly. Yeah.
Okay. So it's basically one fraction times another fraction, which is d times dy over dt squared.
Square.
Because I have dt times dt. Or dt is some infinitesimally small amount, a non-zero, but it's some amount times itself. Is that squared? Unless the math people have been lying to us.
Yeah, I always took it. Yeah, we have to go to the analysis, the calculus definition, h plus the h, and yeah, that could work.
And so, yeah, I mean, even if you went through the basic definition, the
Yeah, the
fundamental
limit- the
definition,
limit
it's
of-
still, it's some amount. I guess it's delta t as delta t goes to 0. But it'd be delta t times delta t, which is still delta t squared.
Okay.
And so, and then from here, that's basically what I have right there. Basically, that is what I have right there.
have to sleep on that.
Yeah, there's a certain amount in physics that seems to play fast and loose with the math.
Yeah, no, that I know, I remember how we step, how you say, that skip it a lot of things the mathematicians will hate. No?
Yeah, physicists, I would claim, do not play fast and loose with the math, they play fast and loose with the notation. So, but the math's legitimate. You can treat dt as, it is an entity, it is some quantity. A tiny quantity, but it's still a quantity. All right, so we get into the resonance, and there's a classic example, so I want to show it to you just because it's a great video. However, it's not an example of resonance, but the reason I'm going to show it to you is that I've seen it in several textbooks. I don't think yours uses it, but I can't remember 100%. Jacobian arrows. Some of you probably have seen it already. We'll find out, well, there we go. Oh, by the way, I don't think I asked you in this class. In any of the videos that I've made, have you seen any ads?
No.
Okay. Because I got notification from YouTube saying they've reserved the right to add an ad to anything.
They're doing that now.
And I was just wondering if they were making money off of my stuff.
They probably will at some point.
Yeah, that's what I'm afraid of. If you haven't noticed it, just let me know. And probably nothing I can do about it this semester, but then I'll start the migration to someplace that won't show ads.
Feel the hall's cooling breath.
Austin, would you be kind enough to kill the lights?
Which one is it?
Please and thank you.
All of them are.
I would say both of them, but it depends on everyone cool. Taking a physics class, of course you're cool. Do you see the person? Right there. Notice he's walking down the node.
just,
Okay, if you'd be kind enough, Austin, to get the lights? Yeah. Please, and thank you. Part of what gets me is that Professor Farquhar was just casually strolling back. And you saw as the bridge was collapsing, the two people who came up at the end, there was one guy running, and then Farquhar just sort of still strolling.
Could he not have driven his car off? Like,
I don't think it was his car, actually. I think it was someone else's car.
he
But-
said, he risked his life for a dog, but I didn't see
Yeah, I
that.
didn't see that.
The dog was in the car.
Yeah, I think the dog died.
Yeah,
Oh.
the only casualty was the dog. Because the dog freaked out when the family bailed, and they couldn't get the dog out, so. They,
That's so sad.
I know, while I'm watching it, I sit over there just saying the dog didn't make it, just so that, I can handle it when I say it. Now, they've had high winds before, and they would close it. I don't know what was special about that time for a car to get halfway for them to go, you know what, this is not a good idea, let's get out of the car now. And it's since been rebuilt, presumably better. All right, so let's talk about why that's not resonance. It's a different engineering phenomena. But if it were resonance, what would have had to have happened? And I guess give a little bit of background. It is over a gorge there, and so there's this, you got the river down there and steep sides. Basically, it's gorge, valley, whatever it is. And so wind comes down through that. In order for that to be an example of resonance, what would have to have happened?
Is it the amplitude getting bigger?
The amplitude did get bigger.
But it would get bigger
Get
each
bigger
time.
and bigger
It would
and bigger.
continue to increase.
And I think the limits of how far it could get were based upon the fact that it was still a solid. It was trying to get bigger, and that's what adds to the strain, which causes the eventual collapse. Think about when I made the amplitude of this get bigger, what did I have to do?
Yeah, put it in there.
So, in the case of that, pardon?
You have to put like an opposing wave to make it get bigger.
More than that. Not necessarily an opposing wave. Let's see, I don't know if I can demonstrate this. So get it oscillating. I go down, down. If I only go in one direction, I can still get the amplitude swinging. All right, so a gust of wind comes and gets it rocking. Relate that to what my hand did with the slinky.
It has to, the gust of wind would have to keep hitting it at the right time, would it not?
Yep. In order for that to be resonance, you'd have to have the wind hitting it at just, you'd have a burst of wind, followed by another burst of wind, followed by another burst of wind. That would be such an incredibly strange phenomenon for wind to be hitting at a particular frequency like that. So it's not resonance unless you get this, and I've never experienced wind that does that. Maybe it does somewhere, it doesn't happen there. It's known as the fluttering effect, and this is the point pre-COVID when I would try to demonstrate it. You can try it at home. You just take a piece of paper and you blow across the edge of it. And what happens, if you blow hard enough, that the end will start to flutter up and down. And so that's what's causing it. And so if you get the constant wind going, you get the fluttering going, and eventually breaks it apart. All right, was there anything else I wanted to talk about with waves?
I have a question.
Yes.
So how did the engineers resolve the fluttering?
I don't know. I suspect it's my solution to everything. You build stronger beams so it doesn't get a chance to move. It seems like the pictures that I've seen, it's more of a solid bridge, which puts stresses in a different spot. I mean, they had it flexible in order to be able to handle the wind, but yeah, I think it's less bendy. And
But
you probably,
it's not damping, it's not.
I don't think that one's a case of dampening. I think, well, it's extreme dampening, I guess, in some sense. That is my understanding of it, of what they did. I was hitting over to, yeah, here. All right, you did that. You did that. Yeah, skip over that, but I usually do. Okay. All right, let's take a small little break. We'll come back. We'll do a little bit of thermodynamics and we'll call it a day. At this point, we've covered everything in the Rube Goldberg test.
So there's not gonna be any thermodynamics in
We're far enough ahead here. I mean, most of the thermodynamic stuff is gonna have to be done on your own. So we'll see, right? I'll let you know before the final. If there are any thermodynamics questions on there, they'd be minimal. Because we still have, because on this test, you got energy, momentum, rotational motion, and then waves. Thermo might be a bit much. Let's go ahead and stop this.